Have you ever worked on tasks or been assigned a project and need to determine what is the longest each task will take and what is the minimum each task would take in order not to fall into any kind of delays? The critical path, the CMP, is one of the two major techniques used to determine a schedule. It is both the oldest and one of the most widely used techniques. The critical path of a schedule is defined as the longest chain of dependent tasks, activities, or deliverables when zero slack or float. It is the change of items through precision diagrams that defines the overall project duration. The task activity or deliverables is the critical path do not necessarily have the greatest risk or the most important, but they do define the earliest finished state of the project. They are 6 key variables used in the critical path methodology. To further understand the critical path, there are 3 steps that go into the creation of it. First is to break the task into operations necessary for the completion. Determine the sequence relationships of each of the operations. The next step is to create time estimates or takt times for each task. These can be early estimates and they can be modified later on. Next is to determine the earliest possible start of each task. Which task must start at the beginning and be finished, what would be the end. Determine the possible starts, early finish, late start, and finish. Step 3 is establish the scheduling variations. Determine a normal start and a normal time. Also a crash start. What is the latest time that a sequence could start and still finish within time? The task activity or deliverables is a critical path. Do not necessarily have the greatest risk or most important, but they do define the early finish states and the projects. And looking at these 6 variables used to the critical path methodology. Starting with the top left portion of this box, we see that there's the early start. This is the early start of the soonest time the project task can begin. Moving to the right is called the duration, the amount of time the task will take to complete. The far right corner is the early finish. The early finish is the soonest time the task can begin. Moving to the bottom left corner is the late start. The late start is the latest time that start can begin. In the middle of the bottom is called the float. This is the slip, the slack, or the amount of time that can be added or subtracted without causing a loss to the critical path. And the far right is called the late finish, the latest time the task can end without impacting the earliest overall time. And the beginning represents the name of the box for the task that's being completed. Now to begin with the calculations, there is a couple of easy calculations that go into it, but they must be followed within sequence. To understand early start, it is taking what we know as the duration of the task, plus the early start. And then we'll add those up, and then we'll do a late start, which is a combination of the duration again, minus the late finish. Taking a look at a critical path, if we call these the sequences of events, and the next steps that follow, we can usually see it, there's a pattern that goes into this. As you look at this critical path, for our example, we've added different durations based on the activities that go into it. The activities also have dependencies. So if we're starting, they would be the start point. But the dependencies for activity number C was dependent on the completions of A and B. As we fill in the activities in the examples, you can see now A has got what the durations are, along with B, representing a figure in time. Could be days, could be minutes. The point is that it shows a sequence of how each of the categories fills in. As we build these, remember the formula of duration of early start is duration plus early start. So in the case of A, we know that the duration is 5, the start time was 0. 5 plus 0 is 5. Taking that over to C, because we know that the activity cannot occur in C until A and B are complete, we begin to understand that having a duration now of the early start as being 5 and the duration is 3, it allows us to fill in the number of 8. As we take these tasks, understanding that sequence C cannot start until A and B are complete, we take largest gap between it. B indicated a 2, where A represented a 5. So we will transfer over the 5 into the C column for understanding the early start. Taking the same formula, 5 for early start, 3 for duration, we get a number 8. And in this case, as we move back down to the F, which is a sequence of activities that cannot proceed to G until C and F are complete, we see that F has a larger duration. So between the two of these, we will carry over the 10. And we will work our way down until we finish it. But at the end, we will see that there is a large number that has occurred from adding these up through the sequences. Here's more illustration of how the math formula fills in. And in the end, we've determined that the earliest start based on these sequences is 22. Again, this could be minutes, this could be days, whatever the sequence we're working on for this task. So we could say that the critical path to complete from start, that it could be finished, is 22 days as the earliest. Next, we want to figure out what the late start is. What is the latest that it could start and still finish on time? As we build this is a combination of understanding the duration and the late finish time. As we look at our chart, we see that working backwards, as we move from left to right to begin, late start works from right to left. To do the math, we take what we know as the duration. Since early finish and late finish in the last step are the same, we'll transfer the 22 to the bottom right corner. Taking 22 minus 3, we get 19. As we transfer that over, they go both in the top and the bottom. We subtract them. 19 minus 7 equals 12. And in this case, we will take the lower of the numbers between the activities to transfer over back until we work our way back to the end, or the starting point would be. To understand this further, what we've been able to determine is that the latest start is 22 minutes. The earliest finish would need to follow this path to have a late and early start finish. The last component to determine is called our free float. This is the maximum number that activity can be delayed without delaying any succeeding activity. Once the free floats are calculated, the string of critical activities will be identified. This continuing strings of critical activities is called the critical path. To understand free float, we would take G, for example. G would be 12 minus 12 would be 0. In another case, we could look at C, which would be 10 minus 8 would be 2. Now, to understand this further, this is the float in this activity that it could sit idle but still not affect the progression of the critical path, hence why it is called the float. Now, when dealing with a Kanban system, understanding the critical path can be a beneficial tool if you're needing to understand what is the just-in-time inventories and when they can be staged and moving forward. This tool can be a little bit intimidating, but one thing to remember is that it gives you a quantitative way of determining what are the sequence of activities that can be built into your model of your Kanban.